Okay, these are improper integrals with singularities is what they're called, and a few diagrams will help us understand this, but I have to tell you that these are more difficult to identify because we're not in the habit. You know, when we have an integral and one of the limits of integration is infinity or negative infinity, it's clear that something weird is going on there. But in these examples, we have to be on the lookout. And in the past, we could have overlooked this and either been lucky or not been able to do it, and we didn't know what was happening. So let me give you a few examples here first, and then I'll come back and look at the bigger generality and how we deal with them. So for instance, here's an example of an improper integral. The integral from 0 to 4 of 1 over the square root of x with respect to x. You know, and at first look, we just start going in and we'd write 1 over the square root of x is x to the negative 1/2 power, and we'd just start going. But the problem here, see, the problem is this integrand is not defined for this x value, is it? So this is an improper integral. What we're integrating is not even defined at one of the limits of integration. Now, that's not good, and we might have overlooked that. Well, here's another example. The integral from 0 to 1 of the natural log of x with respect to x. Now, if we were looking at only a indefinite integral, then the integral of natural log of x with respect to x, remember, we'd have to use integration by parts, and we might just start in doing that. But here again, because we're dealing with a definite integral, there's other things going on. And this one more time, another example is the natural log of x isn't even defined for the x value of 0. Natural log of 0 is undefined. And so we might have overlooked that. And that's my point. We might have overlooked it. Let's look at this example. If we have the integral from negative 2 to 1 of 1 over x with respect to x, then, you know, we feel like we could just jump in. That doesn't look unusual. We go right ahead, no problem at all. And certainly 1 over x is defined when x is negative 2, and 1 over x is defined when x is equal to 1. But we're overlooking is 1 over x is not defined for one of the values between negative 2 and 1. See, 0 is between negative 2 and 1. This function is not even defined between those two x values in place between those two x values. So this is an improper integral. See, it's harder to identify, isn't it? Well, I guess I've made my point that these are not so obvious. We have to be on the lookout for them. Okay, we have to be on the lookout. So here's how we're going to deal with this. There's kind of 3 scenarios. I'm calling them cases. Okay, case 1 looks like this. We're asked to integrate from A to B f of x with respect to x. Now, here's the piece that is we have to observe. F of x is undefined at x equal b. So, kind of a little diagram to illustrate this. And that's all it is. I'm just making a diagram to illustrate it. Nothing specific about this diagram. So suppose this is where A is. We'll just come over here. Suppose this is where A is. A could be positive. I'm showing it negative. And this is where B is. And the type of singularity that the type of discontinuity here, see, it's not defined at B, but it's defined at everything between B, A and B. Okay? So we can use everything between A and B, but just not B. And so it might look like this. I'm being a little imprecise here because f of x is defined okay, it is defined from A, including A, up to B, but not including B. And so whatever this function looks like, at this position, we have an infinite discontinuity. So that's what we mean by infinite discontinuity. It's not defined at B, and it's going to, B is basically a vertical asymptote. So what we're doing is we're looking for, if we were thinking of this geometrically, we're looking for an area, in this case, where the area is unbounded in the upward direction. It could be unbounded in the negative direction as well. Okay, but we're looking at something like that. So here's how we calculate it. We can't, since the function's undefined at B, but all the way up to B, what we're going to do is we're going to integrate from A to C, where C is some number smaller than B. So it's like C is right here, okay? Here's where C is. We're going to get, and the function is defined there. So we're going to integrate from A to C this function f of x. But what we've got to do is we've got to let the C get closer and closer to this value B where we're undefined. So C is approaching B from which side, the left or the right? The left side. So we mean we're approaching B from the left side. So we set up a limit in this fashion so that we can calculate the integral, the improper integral. Okay, here's the second scenario. In the second scenario, the second case, is just in the opposite direction. In this case, we're dealing with the integral from A to B again, where the function, okay, f of x is defined at, not at A, but from A to B. Okay, f of A is undefined. Well, like I said, that's just kind of a reversal of what we talked about over here in the first case, is that maybe here's our A value and here's our B value, okay, and more or less we have a vertical asymptote here, and we don't really know what the function looks like all over, but we're just interested in what it looks like between A and B. And so maybe it does something like this. Okay, we really don't know what it does, but what we do know is that A, we have a singularity, an infinite discontinuity. So the way we're going to set this up, this is where A is, we're going to find some value between A and B called C. And then we're going to let C get closer and closer to A, okay, so that we can find the integral. So we're going to set this up where we're integrating from C to B. B is an okay value. See, B is an okay value. We're going to integrate from C to B of this f of x. But that's not really the value we're interested in. We need the C to get closer and closer to A, so C is going to approach A, but it's bigger than A, so it's approaching A from the right-hand side. So it's a right-sided limit. That's how we'll set that up. Now, case 3 is more or less, I mean, well, case 3 is more or less the kind of the third example I have above. And that would be that if we had a function, f, and maybe here is where A is, and here is where B is, and somewhere between A and B, this function has an infinite discontinuity. Okay, but we're wanting to integrate from A to B. Well, this is kind of like what we did before. See, this is kind of like what we did before. Maybe we'll call this value C, where we have this infinite discontinuity. So we're integrating from A to B, but the function is defined at one value, it's undefined at one value between A and B, but it's defined at A and it's defined at B. So what we have to do is like we did with the infinite integrals a little bit earlier, we break this into two pieces. We'll integrate from A to C, and add to that the integral from C to B. And as we integrate from A to C, remember it's not defined as C. So this would be, we refer to case 1 on how we do that particular integral. In the second integral, remember it's not defined as C. So that would be similar. The letters are different, but it's not defined at the left value, is it? Okay, the lower value. And so we would refer to case 2 above on how we deal with that. So case 3, where it's undefined in between A and B, we have to break into two integrals and go with our old work. Okay, go with what we did before. We create two different limits. Well, let's look at some examples now. So I think this is an example that I started with on the other page, although I mentioned that it was an indefinite, an improper integral, pardon me. So in this case, we're asked to determine if the integral converges or diverges, and of course, if it converges, we want to know the value of the integral. Okay, so, and we notice that this is improper because at the limit of integration 0, the function where we're integrating is not even defined at all. So remember what we've got to do here. It's not defined at the lower value. So we're kind of thinking, in fact, I'll draw a little sketch in this case, what this graph actually looks like. It looks kind of like this. Let's say this is where 1 is, and of course 1 over the square root of 1 is also 1, so that'd be here. But anyway, it looks something like this. It actually gets close to this y-axis pretty quickly, and it doesn't get close to the x-axis as quickly. That's kind of, I don't have a great diagram here, and we're integrating from 0 to 4. Let's say 4 is about out here. So say it's unbounded there, but this is the integration that we're doing. It's bounded on this side. We don't go infinitely to the right, but our region is unbounded above, isn't it? Say it goes up and up and up and up. Okay. So what we're going to do, remember, is since we can't actually evaluate at 0, we're choosing some value here between 0 and 4, I'm calling it C, and we're going to make that value get close to 0. Okay? It's approaching 0, and it's approaching 0 from the right-hand side, isn't it? Approaching 0 from the right-hand side. So here's how we set it up. The improper integral from 0 to 4 of 1 over the square root of x with respect to x is going to, what are we going to do? We're going to find an integral from some value c to 4, where c is between 0 and 4. And we're going to evaluate that integral. But when we do, we're going to take the limit as c gets closer and closer to 0, but it's got to get closer and closer to 0 from the right-hand side. So c is going to be positive, isn't it? Okay, always positive. Well, now we've got to worry about integrating 1 over the square root of x. And we'll evaluate then from c to 4. So when we're integrating 1 over the square root of x, we're really thinking of integrating x to the power negative 1/2, aren't we? So that's 1 over the square root of x. And when we do that, we'll get what? X to the 1/2 power, and the reciprocal of 1/2 is 2. So what we really have here, when we integrate, is 2 times the square root of x, isn't it? Okay. Now this is a c down here, not the 0. Okay. Now, in this case, when we evaluate 2 times the square root of x at 4, we'll have 2 times the square root of 4, which is 2 times 2 or 4, minus 2 times the square root of c. We're replacing x with a c. Okay, well, what's going to happen here? Well, this is pretty straightforward in this particular case, because we might have been lucky and gotten the right answer by doing it incorrectly, but we need to do it correctly. And as c goes to 0, what's happening here? And remember, c is positive, so it makes sense to take the square root of it, doesn't it? See, c is going close to 0 from the right-hand side, so c is positive. Well, as c gets closer and closer to 0, so does the square root of c, and so the limit in this case is just 4. Oh, very interesting. So this area, although it is unbounded in an upward way, has a finite area. So this converges, and it converges to 4, has a value of 4, doesn't it? Okay, value of 4. Well, let's look at the second example that we saw on the other on the previous page, and I think it's rather lengthy because of the techniques that we have to use. So let me start this up on the next page. No, I tell you what. No, I think yes. Okay, here we're to evaluate the integral from 0 to 1 of natural log of x with respect to x, or state that it diverges. And again, this is one of those that we may overlook that it's an improper integral because it doesn't look so strange, but natural log of x is not defined when x is 0. And so that's what causes the issue. Now, what does this graph look like? Well, remember what the natural log graph looks like. If this is where 1 is, the natural log graph looks like this, doesn't it? So what are we doing? We're integrating from 0 to 1, and so, if you will, we're dealing with this particular area that is unbounded below. Okay. Now, the function is not defined at 0, so this is similar to what we did just a moment ago. We're going to pick some value c that is between 0 and 1, and we're going to let that c value get closer and closer to 0 because we can deal with this integral. That's certainly bounded there, isn't it? So the integral from 0 to 1 of natural log of x with respect to x is going to, first we're going to say, oh, that's the integral from c to 1 of the natural log of x with respect to x. Okay, I'm calling it c, we'd call it any constant value, and we're going to let the limit, we're going to take the limit of that as c approaches 0 from the right-hand side. Well, the indefinite integral of the natural log of x with respect to x, we have to use integration by parts. Okay, and I'm just reminding you of that. We use integration by parts. And maybe this is a good time to review. I'm going to move on. When we do that integration by parts, we get x times the natural log of x minus x. So we have the limit as c approaches 0 from the right-hand side. The indefinite integral is x times natural log of x minus x, and we're evaluating from c to 1. Okay, so after we do our evaluation, then we'll worry about our limit. Well, when we evaluate at 1, we'll have 1 times the natural log of 1 minus 1. Minus, we evaluate at 0, we'll have 0, I looked at that and thought it was a 0, it's a c, isn't it? C, my bad, times the natural log of c minus c. Well, some simplification. Remember, natural log of 1 is 0. So this is the limit as c approaches 0 from the right-hand side. What do we have in that first position? We have a 0 minus 1, which is minus 1. And then we have a minus c, natural log of c, and minus a negative c, which is plus c. So when we're looking at this limit, notice what we've got. The limit of the first term, negative 1, just gives us a negative 1. Then we have minus the limit of the second term, which of course is c times the natural log of c, as c approaches 0 from the right, plus the limit of c as c approaches 0 from the right or left. The limit of c as c approaches 0 is 0. So our problem is down to calculating what the limit of c times the natural log of c is as c approaches 0 from the right. And of course, if you look at this limit as c approaches 0 from the right, we have a form where we would have a 0 times a negative infinity. See, the limit, the natural log of c approaches negative infinity as c gets closer and closer to 0. And we can just see that in the graph above. So that's an indeterminate form, isn't it? But it's not an indeterminate form that we can use L'Hopital's rule on. See, to use L'Hopital's rule, we have to either have 0 over 0 or a plus or minus infinity over a plus or minus infinity. So remember how we deal with this. We rewrite this algebraically. We're very clever. And we're going to take this expression, I'm going to put it in brackets here, and we rewrite c times natural log of c as natural log of c divided by 1 over c. That's exactly the same thing algebraically, isn't it? Except now the indeterminate form is a negative infinity for the numerator, and as c goes to 0, the denominator, 1 over c, is going to infinity, a positive infinity. So this is a form, an indeterminate form, where we can use L'Hopital's rule. So to calculate this limit using L'Hopital's rule, we take the limit as c approaches 0 from the right-hand side of the fraction, which is the derivative of natural log of c, and the derivative of natural log of c with respect to c would be 1 over c, wouldn't it? So 1 over c. But the derivative of 1 over c is going to be negative 1 over c squared. You can verify that without any big deal. And so when we simplify that expression that we have, that we're taking the limit of, we actually just get the limit of negative c as c approaches 0 from the right-hand side. And of course, as c is approaching 0, we get 0, don't we? So we have negative 1 minus 0, or negative 1. So this converges, and it converges to a value of negative 1. So the limit does exist. Now, I know it's real tempting. You could actually ignore the fact that this was an, I'm sure that's clear, that's a 0, and this is a c. We could ignore the fact in this case, and like in some other cases, that this is an improper integral, and we might get lucky and get the right answer. But on test, I may ask questions in a way that you have to recognize that this is an improper integral. And just because we can get the right answer by doing it wrong doesn't mean we should do it wrong. So I warn you to do these things properly. Improper integrals have a particular way that we evaluate them. Well, I have 2 or 3 more examples before I complete this section and the discussion. pardon me, you can see here that we're, in this problem, we're to calculate the circumference of the circle, x squared plus y squared equal 1 by calculating the arc length. Now, of course, we know how to calculate a circumference with a formula, but here we're going to use calculus. And so, like I said, we're going to use, the problem says we're going to use the arc length formula, the way we calculate arc length. Now, notice I said revisit. And the reason I said revisit is because we've looked at this problem before, but when we did, we ran into some problems when we tried to, we had to do something a little bit special because we ran into some problems. So first, let's decide that the way the arc length formula looks, okay, S for arc length, or L we could say, is the integral from A to B of the square root of 1 plus the derivative of y with respect to x squared. And of course, we're integrating with respect to x. So this implies to us that we've got to find the derivative of y with respect to x, and we have to decide, furthermore, whether what our a and b are, from where to where. And so, you know, there's some issues to deal with. That's my main point I'm trying to make, and doing it pretty sloppily. Well, one thing that we could do, okay, one thing that we could do here is that to find the derivative of y with respect to x, I suppose we could use implicit differentiation. But what I'm choosing to do is I'm going to solve x squared plus y squared equal 1 for y, okay? And so when I do, of course, I'll get y is equal to the square root of 1 minus x squared. Now let me say here also that usually we would say plus or minus, but I'm going to restrict the part of the circle that I'm looking at is for the top semicircle. Okay, the top half of the circle, and in that case the y's are positive. We've seen that idea before, haven't we? So under those circumstances, then here's how I'm going to calculate this. Okay, oops, s is going to be the integral from 0 to 1. So I'm letting my x's go from 0 to 1, which means that I'm going to be calculating the length of the arc like this, see? Starting at an x value of 0 and going to an x value 1. So it will be this part of the circle that I'm going to calculate the arc length of. And then when I get finished, of course, I'll multiply that by 4. Okay, so this is the way we'll, of course, set up this integral then. The integral from 0 to 1 of the square root of 1 plus, okay, now the derivative of y with respect to x in the circumstances we have here, and you can verify this, is going to be, I'm going to run out of room here. It's the numerator's the opposite of x divided by the denominator, which is 1 minus x squared, square root of 1 minus x squared. And of course, we're squaring that. Okay. So in here, I've got the derivative of y with respect to x. And, okay, now, of course, when we square that, so in our next step, we'll have the arc length as the integral from 0 to 1 of the square root of 1 plus x squared over 1 minus x squared. And we square that derivative. Now, here's the problem that we ran into the first time we looked at this. We thought about doing this, but the problem that we have here is, notice that for the x value of 1 in our integration, under the radical, we have a fraction that has 1 minus x squared. So we would have a fraction that is undefined underneath that square root. Okay? And so we couldn't use this technique when we did this the first time. What we did the first time is we had to integrate from x equal maybe 1/2 to 1. Well, actually it wasn't 1/2. It was square root of 2 over 2. anyway, we had to manufacture a way to do this, and then we actually multiplied by 8. So we, instead of taking a half of the circle, we took a quarter of the circle that would have been, this is the 45-degree line. So we would have taken, instead of a quarter of the circle, pardon me, we took an eighth of the circle. And in here, then we, except I'm doing it backwards, my bad. We came up with this part of the circle, and from 0 to this x value wasn't a problem. But we're going to go ahead and integrate from 0 to 1, and then we're going to multiply that result by 4. But this is an improper integral, just for the exact reasons we discussed earlier. Now, one of the things that we can do here, I believe, is let's simplify this radical before we move on. Okay, let's just do a little bit of work before we move on. So I'm going to move over here. We can write 1 as x squared over x squared, can't we? X squared over x squared. So we have the integral of from 0 to 1 of the square root of, excuse me, we need to write 1, my bad, not paying attention to myself. We need to write 1 that's under the radical as 1 minus x squared over 1 minus x squared. And then we have plus x squared over 1 minus x squared under the radical. And of course that simplifies to just 1 over 1 minus x squared, doesn't it? Is that right? 1 over 1 minus x squared. Okay. So we have the integral of the square root of except 1 over 1 minus x squared with respect to x. Well, then furthermore, we can simplify the square root of 1 over 1 minus x squared as 1 over the square root of 1 minus x squared. Now, again, this is an improper integral because, of course, the integrand is undefined at the x value of 1. So we have to set this up as a limit. So we'll have the limit of the integral from 0 to some value b, where b is, here's the idea, b is here, and 1 is here, and we're going to have b approach 1. So we're finding bigger and bigger pieces of this arc, aren't we? That's what's happening. Oops, until we get to there. Okay. So, of the square, 1 over the square root of 1 minus x squared. And of course, we're letting b approach 1, and it's approaching 1 from the left-hand side. So that means it's always smaller than 1, and so we have 1 minus a number close to 1 but smaller than 1 being squared, and so that's going to be a positive number, and the square root makes sense. Okay, so it all fits together. Then we must recognize that the integral of 1 over the square root of 1 minus x squared is an inverse sine result, isn't it? So this is the limit as b approaches 1 from the left-hand side. Well, the indefinite integral of 1 over the square root of 1 minus x squared is inverse sine or arc sine of x. And we're evaluating that from 0 to b. Okay. Well, what next? Well, let's see. Let's do the evaluation. So we have a limit as b approaches 1 from the left. We substitute b minus inverse sine of 0. Okay. Well, what's the inverse sine of 0? Inverse sine of 0 is 0 because the sine of 0 is 0, correct? Okay. Now, in this limit, as long as this is continuous at 1, which it is, the inverse sine, this should be equal to, then, the inverse sine of 1. And the inverse sine of 1 is the angle, with appropriate restrictions, the angle that we take the sine of to get 1. And of course that value is, now we do this as real numbers, that value is pi over 2. So the inverse sine of 1 is pi over 2, hence the limit, the original integral is pi over 2. Well, remember, this is just a quarter of the circle. So the circumference is 4 times the 1/4 of the way around, and that pi over 2 is 1/4 of the way around. And of course that simplifies to 2 pi, doesn't it? And we know that the circumference formula is what? 2 pi times r? And in this case, of course, the radius is 1, and so we see, oh yeah, we get exactly the same result. Okay. Well, maybe this is where the formula came from. So maybe using calculus is where this formula came from. But we've got our result, and it is an interesting way to approach that problem. Well, I'd like to draw some conclusions here at the end, and actually I've got a couple more problems that I'd really like to do, so I'm going to do that. Let's start those on the next page. And to set up the last thing that we want to investigate, I'm going to give 3 different examples here. And in some cases, we've actually shown the results. Other cases, you're just going to have to accept it. So the first example is the integral from 1 to infinity of 1 over x squared. And so I've drawn a diagram of, and you can verify that my graph is fairly accurate here. Of course, when x is 1, then 1 over x squared would be 1, and so that's this point that we've got here. And when x is 2, 1 over x squared would be 1/4, and so that's the point we've got here. And then we'd have a 1/9 and then a 1/16, and so it gets close to that x-axis fairly rapidly, doesn't it? And so now, just to illustrate geometrically then what this would be, this integral, is it would be the area, if it converges, of this unbounded region, because we're going to infinity. And in fact, I will tell you this does converge. Okay, this does converge, and it's not difficult to figure out the result of that. I believe is 1. Okay. Okay, let me show you a second example. Okay, the second integral I want to mention here is the integral from 1 to infinity of 1 over x to the first power with respect to x. Oh, and by the way, yes, that integral is 1 above, okay? So that's the reason it converges. In this case, we could go through the process and we'd find out that this diverges. Well, there's not much difference there. Let's look at the graph. Integral from 1 to infinity of 1 over x. I've graphed 1 over x here. And you can see, of course, we would be talking about this unbounded area. Now the issue here is how quickly 1 over x squared gets to the x-axis compared to how quickly 1 over x gets to the x-axis. 1 over x squared, you see, gets to the x-axis real quickly. So that area doesn't become smaller. I mean, we're looking at a lot smaller chunks of area above than we are below, and so it does. I mean, maybe it makes a little sense now, although it's unbounded to the right in either case. We get so close to the x-axis so quickly with the first integral that we are virtually there very quickly, but not there. Okay, so that gives us a pause. It would be a question then, maybe, is when does, that is, for what values of p, the integral from 1 to infinity of 1 over x to the power p converge. Now, of course, we got to assume that p is a positive number so that we really do have a fraction. So we see above, if p is 2, it converges. If p is 1, it diverges. So it would be nice to know if we could come up with some idea for what p's does this in fact converge. And so the way we would go about doing this is we would just start our job, okay? And our job would look like this. Let's calculate the integral from 1 to infinity of 1 over x to the p, assuming p is a positive number. It doesn't have to be an integer, just a positive real number. Well, we go through the same process as that we would have to set up a limit, and it would be the limit as, in this case, we're going to integrate from 1 to b and let the b go to infinity, okay? And we're integrating from 1 to b, 1 over x to the p power. Well, the integral of 1 over x to the p power is going to be x to the power p plus 1 divided by p plus 1, or multiplied by the reciprocal of p plus 1. So that's the integral. No, my bad. We actually are integrating x to the negative p, aren't we? And so it would be x to the negative p plus 1 divided by negative p plus 1, or 1 over negative p plus 1. And we could write that a little bit better. We could say, okay, we could say that this is 1 over 1 minus p, instead of saying negative p plus 1, and we could say it's x to the power 1 minus p. That would just make it a little easier to work with. So what we've got then is the limit as b approaches infinity. And remember, the integral we just calculated is 1 over 1 minus p times x to the power 1 minus p. And we have a definite integral, so we're evaluating that from 1 to b. Okay? Well, where does that lead us? Well, we evaluate, of course, our x at b. We could factor out the 1 over 1 minus p, since that's just a constant. And when we evaluate at b, we get b to the power 1 minus p, minus, we evaluate at 1, we get 1 to the power 1 minus p. Of course, we can factor out that constant 1 over 1 minus p so that we can deal with calculating this limit. And of course, in this limit, we've got a b to the power 1 minus p minus a 1 to the power 1 minus p, but that's just a 1, isn't it? So the whole question ends up being, when does this limit exist? And so that would be the question about when does the limit of b to the power 1 minus p as p approach infinity, when does that exist? When is that not infinity? Well, here's what we have to worry about. If 1 minus p is positive, see, if 1 minus p is positive, let's think about this. If 1 minus p is positive, then we have nothing more than the limit of b to a positive power, and b is approaching infinity, and so that would be infinite, wouldn't it? So in this case, the integral from 1 to infinity of 1 over x to the p power would diverge. Does that make sense? Well, look what that says, okay? Look what, in fact, it would diverge. Now, let me also say something. I'm assuming in this case, see, I assumed the way I did this integral, I assumed over here that p was not 1. See, I made that assumption because if p is 1, we don't use the power rule, does it? 1 over just x, we integrate that, we have to use natural log of x. And so in the case that p is 1, that would be up here, and we're going to assume that we can do this, and we find out that it diverges. So here's what we've got then. We know it diverges if 1 minus p is greater than 0, and if we look at 1 minus p being greater than 0, let's just add p to both sides. That would be 1 is greater than p, or p is less than 1. So when p is less than 1, this diverges, but above we also saw that when p is equal to 1, it diverges. So it diverges if our exponent is 1 or smaller, a positive exponent that is 1 or smaller. Now, on the other hand, if well, I've been going along here and drawing, and I'm sorry for the silence. I didn't realize that I was actually recording at the time. As you see, that I want to look at a couple of examples here. And the first example is the integral from 1 to infinity of 1 over x squared with respect to x. And what you see is my drawing over here on the side. That's the graph of y equal 1 over x squared. And so if we were to look at this integral, which we know is an improper integral, we could interpret the result of being the area of this unbounded region. Okay, you see it gets close. Obviously, when x is 1, 1 over x squared is 1 over 1, which is 1. And when x is 2, 1 over x squared is 1/4. And then when, of course, x is 3, 1 over x squared is 1/9. And so you can see that it's getting close to that x-axis very rapidly. Now, this value is, I don't remember if we've actually done this problem, but the value is actually 1, so this converges. Now, the next example I want to look at, because I'm trying to make some kind of point here in a moment, is the integral from 1 to infinity of 1 over x with respect to x. Now, I'll tell you in advance that this diverges. Now, let me get the graph up real quickly. Get the graph up real quickly. We're going to graph y equal 1 over x. So when x is 1, y is 1. This time when x is 2, y is 1/2, as opposed to above, y was 1/4. Here when x is 3, y is 1/3, so opposed to above where y was 1/9. And of course here, when x is 4, y is 1/4, which would be approximately here, as opposed to above, y was 1/16. So when we graph this, we can see that it doesn't get close to the x-axis nearly as fast, nearly as quickly. Okay, it does get close. And so as we look here, then the area we're talking about would be this area, and only because I've told you, but you could verify it on your own, the value of that integral would be infinite. So we have an infinite area as opposed to above where we have a finite area of just 1. Wow, what a difference. The area above is 1, the area below is infinite. And it has to do with how quickly that graph is approaching that x-axis. Above, it gets close to that x-axis very, very quickly. So for instance, if x was 1,000, 1 over 1,000 squared is 1/1,000,000th. As opposed to below, we would just have a y value of 1/1000th. And so it gets fast, it gets close to that x-axis so quickly that the limiting process gives us a finite number and is in fact only 1. Now, here's the question really. Assume we have some number p that is a positive number. And the question becomes then, for what values of p does the integral from 1 to infinity of 1 over x to the p power converge? And for which does it diverge? And for what values does it diverge? Now see, and p needs to be positive, otherwise we would have 1 over x to a negative exponent would just be x to a positive exponent, and that's not what I'm interested in. I want to make sure we really have a fraction. So above we can see, in this case, p is equal to 2, isn't it? And in that case, we converge. In this case, p is equal to 1. That's the exponent on x, isn't it? And in that case, it diverges. So the question is, can we determine when it will diverge and when it will converge, or vice versa? So we go about just doing our work. The way we would start out is we'd look at the integral from 1 to infinity of 1 over x to the p power. And we'd know that we had to do this, that's an improper integral, so we'd have to create a limit of an integral. And of course, what we're going to do is replace infinity with some constant b, and we're going to let our b value go to infinity. So this is what we're actually dealing with, okay? Now, to do the integral, I'm going to maybe skip a few steps here, potentially. To do the integral, we really think of 1 over x to the p as x to the power negative p. And when we do that, we would end up with x to the negative p plus 1 divided by negative p plus 1, or times the reciprocal of negative p plus 1. And I'm going to write negative p plus 1 as 1 minus p. So actually what I'm going to do over here is I'm going to say this is 1 over 1 minus p times x to the power 1 minus p. And that's the result of our indefinite integral. We've got to evaluate that from 1 to b. Now, in all of this business, p is a constant. You know, we're just trying to figure out some information about p, but p is a constant. So I'm going to factor it all the way out here. And so we're going to have the limit as b approaches infinity, and when we evaluate, say, x to the power 1 minus p, at b, we'll have b to the power 1 minus p, and then we'll subtract, and when we evaluate at 1, we'll have 1 to the 1 minus p. But of course, 1 to the 1 minus p is certainly going to be equal to 1, isn't it? Oh, and by the way, up here I assumed that p was not equal to 1. Otherwise, we just have 1 over x, and we wouldn't integrate it using the power rule at all. We'd have to introduce natural log, wouldn't we? But we already know for p equal 1 that we diverge from above, and I didn't prove that, but you can do that on your own, okay? Now, here's where we are. We have to kind of stop and think about what's happening here. If 1 minus p, that's this exponent, is greater than 0. See, if 1 minus p is an exponent that's bigger than 0, then that would say that the limit of b to the power 1 minus p as b goes to infinity, it says we have some number to a positive power, and that number is getting larger and larger, so this would be equal to infinity, wouldn't it? So that would mean, in this case, that the integral from 1 to infinity of 1 over x to the p power with respect to x diverges. It diverges. Now, what is 1 minus p greater than 0 mean? Add p to both sides, that'd be 1 is greater than p, or a more convenient way to write it, when p is less than 1. Now, from above, okay, from above, we already know it diverges when p is equal to 1, so it only diverges when p is less than 1, but from above, we can say when it's less than or equal to 1. Now, on the other hand, if 1 minus p was greater than 0, then what we would have, see, we'd have 1 minus p is a negative exponent, is negative, so that means this exponent would be negative when we're looking at this limit. Well, if the exponent is negative, then what we would end up looking at is, why don't we have the negative of that exponent? So in other words, why don't we rewrite this as 1 over b to the power, the opposite of that negative exponent, which would be p minus 1. See, p minus 1 is a positive exponent if 1 minus p is a negative exponent. Now, in this case, what's going to happen? We've got this b, we got this fraction where the b value is positive and getting larger and larger, and the p minus 1 exponent is positive. Okay, it's a positive exponent, it's not changing, so we have a denominator that's getting larger and larger. Here we actually have a limit of 0. So what do we conclude from that? Well, that tells us that the integral from 1 to infinity of 1 over x to the p power with respect to x converges as long as 1 minus p is greater than 0. But what does 1 minus p greater than 0 mean? Add p to both sides. That means when, whoops, I wrote that backwards, didn't I? My bad. I'm sorry. We already looked at 1 minus p greater than 0. We're looking at 1 minus p less than 0. Okay, my bad. And if 1 minus p is less than 0, that's what we're trying to say. That's a negative exponent. And if that's a negative exponent, this is a positive exponent. I wrote it down incorrectly and then referred to it correctly. So we would still get a limit of 0, so the entire, improper integral from 1 to infinity of 1 over x to the p converges whenever 1 minus p is less than 0. Well, what would that mean? We'd add p to both sides, and that'd be p is greater than 1. So that would be true when p is greater than 1. Okay, it'd be true when p is greater than 1. So we've kind of answered this question. Not kind of, we've answered this question. This integral converges if p is greater than 1. Well, up above, p was 2, greater than 1, it converged, didn't it? And it diverges when p is, remember p is positive, so it would have to be bigger than 0, but when p is less than or equal to 1. Well, above, of course, we have p is equal to 1, and it diverges. And one of the problems that we did earlier, kind of really junking this up now, one of the problems that we did earlier is we considered the integral from 1 to infinity of 1 over the square root of x with respect to x. And if you recall, I think we said that that diverged, didn't it? We said it diverged. And if we rewrite this, square root of x is x to the power 1/2. Here we have a p of 1/2, which is less than or equal to 1. And so we would have anticipated at this point that that would diverge. And we kind of have a formula for deciding when it's going to diverge or not. Now, about the convergence, we can only tell whether it converges. We can't tell specifically. We could maybe come up with a formula, but we haven't done that yet, or we haven't done that at all here to know what it actually converges to. This is helping us just determine convergence or divergence. So that becomes important. Well, it would be, we would also, on the next page, let me do one more thing. I keep telling you that we're continuing. Let me do one more thing. Now notice here it's the same two functions, but this time I'm integrating from 0 to 1, and this is these are both improper integrals again because the integrand is not defined at 0. We have a singularity of 0, infinite continuity. And in this case, I'm not going to be as precise as I was a while ago, but maybe you can see something begin to appear here. So here's 1, here's 1, here's 2, and 1 over x squared is 1 when x is 1, okay? When x is, I haven't done a good job at all here. When x is 1/2, then 1 over x squared is actually 4, and it's way up there. So what's kind of hard to tell here, because I haven't done a good job of showing this, it goes like this. See, it goes like this. And what we're doing is we're trying to figure out, if you will, maybe this area, okay? And because of the way this function works, it doesn't get close to the y-axis very rapidly. Now, it got close to the x-axis rapidly, but it doesn't get close to the y-axis rapidly. This diverges. Oh, that's strange. Now, on the other hand, if we look at this graph, okay, when x is 1, y is 1, this is 1, this is 1, this is 2. When x is 1/2, when x is 1/2, in this case, y is 2. And so what we're going to see, notice this gets close to that y-axis much more rapidly, okay? And anyway, much more rapidly. And so, and it may not be clear here at all, but in this case, this actually converges. It's kind of the opposite scenario, isn't it? And it's because what happens close to the y-axis as opposed to what happens close to the x-axis. And we could come up with a similar rule here. Maybe this was overkill, didn't really need to do it, but I just wanted you to be aware that we can't always anticipate what's going to happen when we talk about improper integrals. Well, that's all I've got about improper integrals, and it seems like I kind of took this on and on. Good luck on your homework.